Okay, let's get back to stuff. Any questions so far? Okay, so we just talked about these things called... Yeah, go ahead.
Why don't we have a rule of x equals to y a?
You could. So, but the thing is, you have to be consistent for that. So that actually will lead us into something useful. So let's take your question into consideration. What if we have the 4 types of rules we had before, but I allow you to have another rule of type where the terminal's on the right side of the variable. Okay? So instead of just the left side, you can also have the right side as well. So what could... Yeah, okay, let's see. So I'm trying to remember the example. So let's see. So I can have, let's make this grammar. Okay, so this is going off the question where you can have a terminal on the right side in addition to the terminal on the left side. So if you have terminals only on the left side, that's called a left regular grammar. And if only on the right, you can guess it's a right regular grammar. So here, what do you think the language is of this grammar?
Is that T to S1?
T to S1. Mm-hmm. What is the language of this grammar, do you think? 0 to the n, 1 to the n. And why do you think that's the case? Mm-hmm. Right. So let's see. If I go with S and I say, yeah, I want to apply that 0t rule. So 0t, and then t is forced now to make the S1 rule. So that must mean I have 0s1. But then I just generated one character on one side and a character on the other side, which means that I can repeat this procedure as many times as I like to get some number of zeros followed by the same number of ones after it. So in fact, that subtle change will get us a non-regular language, which is pretty interesting. There's a class of grammars where you have only one variable on the right-hand side, but we're just going to fully generalize here and say you can put anything you want on the right-hand side. Okay, so what these are called context-free grammars. So a context-free grammar, CFG. So it's just a normal grammar where you have the variables, terminals, start variable, whatnot. But here we have the rules allowing you to replace any one variable with anything. So any combination of terminals or variables in any order, as many as you want or as little as you want. So it's a grammar where the rules are of type, so it's going to have some variable x going to some w, where w can be any combination of variables and terminals in any order. So w is a member of v union sigma star. So as many as you want of variables or terminals in any order you like. So in fact, the grammar we just had right here is a context-free grammar. Well, let's see. Is every regular grammar a context-free grammar? Yeah, because context-free grammar just says, yeah, you can have any rule of any type. The regular grammar just says you have to have it of a specific type. But otherwise, the definition is exactly the same. So we can see from this that every regular grammar is a CFG. So we're going to call a language L a context-free language if some CFG generates it. So by this logic, 0 to the n, 1 to the n is a context-free language because I just gave you a context-free grammar for it. And we're going to call this abbreviation CFL. So what we wanted, as I mentioned at the beginning, is some layer in between regular and this really big class of decidable languages. Is this actually a layer in between? Well, let's see. Is every regular language context-free? Yeah. Well, and how do you know that? Right, because of that fact right there. So this fact right here tells us that every regular language is context-free. So let's write this down so we don't forget. So every regular language is a CFL because every regular grammar is a CFG. But is the converse true? Not the contrapositive, the converse true. Is every context-free language also a regular language? No, and what's the counterexample? 0 to the n, 1 to the n. So 0 to the n, 1 to the n is a CFL, but not regular. Okay, does that make sense? It's just a natural generalization where you just put anything on the right-hand side, and as a consequence, we get, in fact, more than the regular languages. It's a lot harder, and we'll eventually show that there are decidable languages that are not context-free, but we'll get there eventually. Okay. So, do we need an example, or is this example enough? So just note that you can have anything on the right-hand side that you like. So I can have, for example, 0, S, 1. Actually, let's do one example. So what does your compiler do at its first stage when it looks through your program, and what is the first error that commonly comes up? Like say Java, for example. So like it immediately comes back and it tells you that you have a mismatched parenthesis or a mismatched curly bracket or something, right? So what the compiler is actually doing is it's checking that first and then doing like all the lexical, semantic, and whatever analysis. So could a context-free grammar check, do you have a balanced set of curly brackets? So if we have a curly bracket like this, or a set of curly brackets in this form, is this a set of balanced curly brackets? Yeah, because if we look here, that's balanced, and what is ever in between a left and a right one, if the thing inside is balanced, then obviously the whole thing is also balanced. So in fact, the entire thing is a set of balanced parentheses. Because you can imagine that these curly brackets correspond to the actual ones in a program. So could we make a context-free grammar that generates the set of strings that are balanced curly brackets? Well, let's see. If we have a left and stuff in the middle, and then eventually we see a right, well, what has to be in the middle? Can it be unbalanced in the middle? No, so whatever's in the middle must also be balanced. What about afterward? After that left, after the right one, what should it be? It should also be balanced. So in fact, we're going to be using this and this to make a grammar quite easily. So here's how we do it. So we have to have a variable, s. So the way that we can have this is either there's no characters at all, which is obviously balanced because every left one matches a right one. So either empty, or, well, either I must see a left at the beginning, no matter what. I can't see a right curly bracket at the beginning. Well, what must be in the middle? It must be a balanced set of curly brackets. Well, we're assuming by induction that S could make the set of curly brackets, balanced ones. So let's say that S has to be in the middle. Then eventually we must see a right one. And then afterward, we also must see a balanced set of curly brackets. So S must be over there too. If we omitted that second S, what language would this be? If we just knock that S out. Wouldn't that just be almost the exact same as 0 to the n, 1 to the n? Yeah, because it's just some number of left ones matched with the same number of right ones. But here is something different where I can have a whole different set of balanced curly brackets. So let's just convince ourselves that this is true. Yeah, okay, let's try to generate this string up here. So I got to start with S, and then what rule should I apply? Should I apply the S goes to empty one? No, so I have to apply the other one. Okay, well, let's see. Now I have two variables to pick, right? I have two variables to pick. Does it matter which one I pick? Well, let's see. It says, the grammar says, replace any variable with something on the right-hand side. Does it say which one to pick? No. So that's why it's called a context-free grammar. It doesn't care about the context in which the variable appears in the string you've derived so far. So here, in that string, the two S's, you can replace either one of them with any one of the rules corresponding to S. It doesn't matter which one you pick. Okay? So there are things called context-sensitive grammars, which do depend on the context. But here we don't care about the actual context. Okay, so which one do you want to pick? Let's do the inner one. So I want to replace this guy. So which one should I replace him with? The left, right one also, yeah. So let's see. So we're going to have left, and then I just replaced it with left S, right S. And then we still have the other ones there. So I'm going to mark which one we did. Okay, so now what are we going to do? Which S do you want to work with? How about the right one? Which one? What will that go to? Empty. I want to make that S go away, right? So, yeah, okay. So let's make the rightmost S go away via the S to epsilon rule. S, and then we just made it disappear. Okay, now what? The second S. So what do you want to replace that one with? Well, it better be the left-right one, because we wouldn't actually get the string up here that we wanted. So we still have this business at the front that we haven't dealt with yet, but then we are going to put this, just replace it in like this. So now what's going to happen to all three of those S's? Yeah, they're all just going to go away. So for the interest of time, I'm just going to show the final result, which is the string that we actually wanted. But you can imagine that we can, for example, pick the second one, then pick the last one, then pick the first one. Any order is okay. You can replace any one variable with a rule corresponding to that variable. Does this all seem familiar? Maybe, but yeah, go ahead.
If the sample string you were given was just a set of curly brackets, could we just replace that S at the beginning with epsilon?
Both of them, yeah. Like you mean just one left, one right? Yeah, of course. Mm-hmm. Other questions? Okay, but I should note that you're not given a string. I'm just saying that's the target we want to make, but you're not given one to work with, or to as like input or whatever. Okay, so when we talked about regular languages, we made DFAs and some examples, but what did we talk about with respect to regular languages after that? Well, we noted that regular languages are just, or languages in general, are just sets of strings, right? So what do you want to do with a set of strings? Leave them alone. Well, what do you want to do with a set? Combine them somehow, like union or whatever, concatenation, star. So what are those three? Union, concatenation, and star. What are those three called? Regular operations. And in fact, we'll show quite simply that context-free languages are also closed under the regular operations. So that means if I have two context-free languages, then their union is also context-free. Okay? So in fact, this is actually quite short. So CFLs are closed under regular operations. So I'm just going to note here, union, concat, and star. Cool, cool. So let's do union first. Actually, all three are quite easy. So let's say if L1 and L2 are CFLs, then what we want to show is that L1 union L2 is also a CFL. So I tell you that L1 and L2 are context-free languages. What do you immediately think of? Because they're CFLs, what has to exist? A grammar, right? There must be grammars for each one of them. So let's let G1, G2 generate L1, L2. And then we can denote each of the parts to be V1, sigma, R1, S1, and then 2 for the other one. Well, let's see. What does union mean? It says this or this. So what does that mean in terms of a grammar? Two rules, right? So let's say that S1, S2 are start variables for each of the grammars. Could I have a rule that says I can either go to S1 or I can go to S2? But don't I need a new variable for that? Yeah, so in fact we need a new variable. So let S be a new variable, and then the rule will be S going to S1 or S2. There's a small technical note here that the two grammars you have better not have any variables in common, because if they do, then what could happen is you're in one grammar and you can decide if you wish to go to the other grammar, but obviously that's not desired. But it's a small technical detail. But this is actually quite clear. I make a new variable and I can choose either to go to S1 or S2. Easy. What about concatenation? Oh, it's just S goes to S1 immediately after S2, because that's just concatenation. I make something in S1, and then I can make something in S2, concatenated after. So I'm actually going to put all three eventually here. So S for concatenation is S1 concatenated with S2. Cool, so just make a string in S1, concatenate with a string in S2, whatever it makes. Sweet. What about star? So let's just say we're working with S1 here and not S2 because we only need the star of one language. Well, what string is in the star of every language? Epsilon. So do I know that the original grammar made epsilon? No idea. Is it wrong for me to make one? Make epsilon right here? No, it's never wrong to have redundant rules. So I'm going to explicitly make epsilon immediately. But what else might happen? Well, what does star mean? It says any number of times, pick one string out of the language, concatenate it, and then go through the language again, pick another string, and then at some point stop. Well, what should I do for a grammar here? S1, yeah. Actually, I should do S1 first, then S. Why? Because then I'd be concatenating backwards. Right, because I'd be making the string on the end, then working before that, then before that. Here, I want to make the string at the beginning, then go back, possibly making something else, and then keep going all the way through. So in fact, it's really easy to do all three operations. Even the easy NFA examples were more complicated than this. So hopefully this should make it clear to you that regular operations doesn't mean regular for regular languages. It's just the operation, the structure of the strings underneath all of it. But okay, so any questions on why this is true? It's just playing with the grammars and then just merging the two start variables together. Okay. So let's actually talk about the example grammar in the notes. So this one is, so the terminals here are plus times parentheses and a single character A. So I can have S plus S, or S times S, or parentheses with S in the middle, or A. Okay, that's fine. So let's actually try to generate the string A plus A times A. We can actually ignore the parentheses one if we wanted to. So what's one way we can make this string? Well, what we could do is we can apply the plus rule, then we can apply the times rule on the second S, and then transform all the S's to A's. But it's actually quite cumbersome if we just do these arrows over and over and over. So a more compact way to represent these derivations is something called a parse tree. So a parse tree is just a tree that's rooted at the start variable when you first start making things, and then you're just going to build the tree out based on what rules you apply. So at the beginning, the root is S. Then what one rule could I apply first? How about the S plus S rule? So we're going to have three children on this root, which are S plus S. Okay? And then what rule could I apply next? S times S on which of the two S's? On the right one, yeah. Sorry, I better not apply it on the left one because I want the times on the right side. So here I'm going to do the S times S thing. And then what's going to happen to all the S's that are on the leaves of the tree? They're going to turn into A's. So I'm just going to do all of them at once here. Is there another way to make this string? I'll show you one. So instead of doing the plus first, we're going to do the times first. And then expand the left side. S plus S, and then all the S's go away. Isn't that kind of annoying that you have more than one way of generating a string? So this actually might be interesting if you have a compiler and you want to determine if your program is syntactically correct. So you feed it to this compiler's grammar, and it has to figure out, it has to make this parse tree and say, oh, can I actually make this, the program string that you gave me? And if there's more than one way of generating that string, then your program may be ambiguously defined, or the grammar may be defined in more than one way, in a correct way. So this term for when this happens is called ambiguous. So a grammar, not necessarily a CFG, but a grammar in the general sense, is ambiguous if some string in its language can be derived in at least two ways, distinct ways. So essentially the two parse trees are different. But look at this string again. Especially this parse tree right here, the right one. What am I doing every single time? Well, what I could be doing is I'm going to expand the leftmost variable that I have so far. So let's try to do this in slow motion, where we try to make the parse tree only looking at the leftmost variable in the tree. So I start with S at the top. What is the leftmost variable in this tree? There's only one. So which rule should I apply? Let's do times. So let's do, I should put the times above. S. What is the leftmost variable that I haven't expanded yet? The far left one. So what rule should I work with on that one? The plus one, yeah. So I'm gonna expand this, then plus S. And then I'm gonna expand the left S first with the A, then the next one, which happens to be this one, with an A, and then this last one with an A. And then I generate this string. Is this the only way to do a leftmost derivation? No. Well, what could I do instead? I could have started with plus, and then I could have gotten this exact same other tree that we got over here. But it's just I'm expanding different ones first. But the end result is exactly the same. So the real definition of ambiguous is derived in at least two leftmost derivations. But could we talk about parse trees instead of these leftmost derivations? Because I don't want to make this derivation over and over. If there's a derivation, is there a leftmost derivation? Yeah, because at every point, there's going to be some leftmost variable that you haven't expanded yet. So expand it that way. Because this is a context-free grammar, it doesn't matter which one you actually expand. So in fact, if you have a derivation, there is a leftmost derivation. Okay, well, let's see. If you have a leftmost derivation then, could I make a parse tree? Yeah, certainly. What about the other way? If you have a parse tree, could you extract the leftmost derivation? Yeah, so you just start at the leftmost end of the tree, look up to see if there's a variable right there, then you know which variable you just expanded. And then you go up and then you figure out, oh, look down there on that subtree and see, do you in fact have any leftmost variables? And so you can extract which variables in which order you expanded them. So because the way you look through the tree, you're looking through it in a leftmost manner. So in fact, you can extract the leftmost derivation from a parse tree. So in fact, the parse trees are equivalent to leftmost derivations. So in fact, we can talk about parse trees or leftmost derivations. Yeah.
What was the difference from that work through than the one we did up there?
The end result is not different, but the way we expanded them was different.
So you looked at the very left A times the very right A?
Yeah, so in fact for the one, well, they're the same. If you look at it, what we could do is do the first step and then expand the right one, then expand the left one if we wanted to. But the leftmost derivation always picks the leftmost variable first. Okay? Any other questions? Yeah.
Is this important because we could have like a variable b plus a or something like that? So we need to know like the order in which we are creating the equation.
What do you mean, what is this important?
The going from leftmost derivation.
No, not necessarily, because we're going to be talking about parse trees, and that'll help us prove some results later on. So the key here is that instead of talking about these derivations, which are kind of cumbersome to work with, we can talk about parse trees and just look at a parse tree instead. It's more visual that way. So it makes everything easier. Other questions? Yeah, you could. But leftmost derivations make it, so it's kind of like why we put the terminal on the left side of the variable for the regular grammar. It's so that we can enforce one way, but you can equally talk about rightmost derivations. But the general way people approach this is leftmost. Other questions? Okay, so what you may find annoying, of course, about ambiguity, as we've already said, is there may be multiple ways to generate a string. So, and you may think, well, maybe there's a procedure to figure out, okay, I have this grammar which is ambiguous. Maybe I can convert it to a grammar which is, in fact, unambiguous for the same language. And then if we have an unambiguous grammar, then we can actually generate every string that we want in exactly one way, and life would be nice. But in fact, this is not possible. And in fact, it's doubly sad, as I'm going to say. So there are these things called, so this is just only for your knowledge. I'm not going to test on this. Something called inherently ambiguous languages. So these ones mean that every single CFG for these languages is always ambiguous. Every single CFG for these languages. So that's kind of crummy. But what you may want to know is, okay, sometimes you can't convert a CFG to an unambiguous one. Could we even detect that a grammar is in fact ambiguous, because remember the definition. It says if some string can be derived in more than 2 ways. But is there in fact like a test that we can check? I give you a grammar and you tell me whether or not it's ambiguous. But in fact, that question is undecidable. So checking an arbitrary CFG is ambiguous or not is undecidable. If you have the CSE textbook, this is one of the exercises. So there's an undecidable result that we didn't talk about, but if you want to look in the CSE textbook, this is one of the exercises based off of that result we didn't prove. But it's actually pretty interesting that checking whether an arbitrary CFG is ambiguous is just not possible. Another one that you might want to wonder is, well, we could, based on the P set, there's some technique of trying to minimize a DFA. Like I give you a DFA and you want to minimize the number of states that you have. What about a grammar, a CFG? If I want to like eliminate a rule or check if we have a grammar with 1 fewer rule or something like that, could we actually do that? In fact, that question is undecidable too. So, but in fact, we'll be able to answer some questions about CFGs, show they're decidable, but some we in fact can't. Any questions before we move on to the next big thing? But as I was saying, for the ambiguous stuff, it's kind of annoying that you have some ambiguity in the grammar, and of course, as I said, you can't check whether a grammar is inherently ambiguous or even just ambiguous. But maybe we can try to eliminate some of it. Maybe we can eliminate some of the ambiguity here. So let's look back at the curly bracket one. So what happened here? What happened was that we were expanding these variables out by applying this rule, and then we're going to make this long string, and then what happened at the end was what? We had this long string right here. What happened eventually? It shortened up because all of the s's went to empty, right? And so you may think, well, maybe we can have potentially an incredibly long string and all of it gets shortened up into the empty string right at the very end, which is kind of annoying if you have that type of situation. Another situation that might be annoying is, well, for the grammars that we looked at here, say like this one, we knew exactly which rule to apply at every step if we have a target string in mind. What if we had a really big grammar with really long rules? Do you know necessarily which rule to apply? I could try applying some of them, but I might make the wrong choice at some point. Okay, so what you may want to know is, could we try to make these grammars simple in some sense? And so that's actually what we're going to try to address. So any people in databases? No one. So there are these things in databases called normal forms. I'm not a database person myself, but I know that these things are a way of simplifying addressing a table in a database. And in fact, we're going to apply the same idea here. So we're going to talk about one form, something called Chomsky normal form. So like the biggest known thing about CFGs. So the idea here is, let's make the grammar as simple as possible. And what we want is, we want this CNF thing, so abbreviated CNF. We want this CNF thing to allow us to still describe the context-free languages. So we want to have the same languages at the end. And what would be nice, and we'll show, is could we convert an arbitrary CFG into a grammar that's in this form, that's this really simple form. And so then we can actually say a whole lot about the grammar once we convert it into this form. So what is this form? So a CFG in CNF. I know a lot of three-letter acronyms. TLAs, three-letter acronym, oh, whatever, okay. So a CFG in CNF has rules, of the form. So we're still, obviously we're going to have one variable on the right-hand side, on the left side, and stuff on the right side. So there are three types of rules we're allowed to have. So what I'm allowing you to have is I can have one variable make two variables. Precisely two variables. I can't have more than two. I can't have fewer than two. Exactly two. And what we're going to insist is that B and C on the right side are not the start variable. Okay? So basically what happens is if you're at the start variable and you apply a rule, you're never coming back to the start variable. Okay? Well, I gotta actually get terminals out of this thing. So let's allow you to make a single terminal and nothing else. Okay? So I can either make two variables with any variable, or any variable can make a single terminal, any terminal. So I should say A is a terminal. But since we're dealing with the context-free languages, we gotta deal with our favorite string, which is empty string. So the way that I'm going to allow you to make the empty string is only from the start variable. No other variable can make the empty string. So it seems like a pretty restrictive type of grammar, right? Because even the grammars we've just been talking about, none of them follow this pattern, right? Yeah, we have like other variables making the start variable. We have more than one terminal on the right-hand side, and or just a single variable on the right-hand side. So we need to think about, could we convert any context-free grammar into CNF? And the way that we're going to do that is looking at this example right here, which is definitely not in CNF. But we're going to work with it anyway to try to show how do we actually get to CNF. So this is our example. So S is obviously the start variable. Well, do we violate the first rule form, where you don't have the start variable on the right-hand side? Yeah, we violate that. How do we fix that? Not in CNF, no. Oh, we can always make a new start variable. Okay, so let's make a new start. Oops, I'm gonna make a new start variable. I'm gonna call it S0. Well, what should S0, the new start variable, make? The old start one, right? Oh, did I just fix that issue without changing the language? So we need to actually check, do I change the language here? Well, think about it. If the old grammar had a derivation, do I have one now? A sequence of rules I apply to get some string. Yeah, I just tack on S0 makes S at the very beginning of that derivation. And the other way around. If I have a derivation in this grammar, do I have one in the original? Well, every derivation in this one must start with S0 makes S. And then whatever happens after, I just cut the cut the S0 makes S part at the beginning, and then now I just have a derivation in the original grammar, the sequence of rules to apply. So in fact, I don't change the language here. Cool, so we're gonna call this step 1. So it's gonna be 5 steps, but we'll get there. Okay. And what we want furthermore out of these steps is I don't want to have to go back and fix problems that I already fixed before. Okay? So you could try to do these steps in any order, but you may introduce problems that you fixed before, and we don't want that. Okay, so we checked that one, so that's fine. What other ones are we failing at? Well, one that we're failing at is this one, right? Just only this, so I should mark this here. So S0 is the new start guy. Is some non-start variable making epsilon? Yeah, oh, we gotta fix that. Well, how do I eliminate the start variable? How do I eliminate the epsilon rules? Seems like a problem, right? If I just axed that epsilon rule right there, I just took it away. What's the language of the grammar now? Infinite? It's empty. I don't generate any string full of terminals at all. So I better not just axe all of the epsilon rules. Seems like a problem. Any ideas? Well, I could do that, but if I just do that, then how do I handle the other one? If I just axed it again here, then the only string I can make is the empty string. Oh, what we could do is say, well, let's look at this. I need to remove this first. Let's look at this right-hand side right here. Could either or both or none of those two S's make the empty string? Either both or one of them or none of them. Could I add rules to handle when those cases happen? Well, let's see. If I am at some point and I apply this thing, and now I want to apply the first S going to empty, that's just eventually showing that I get to this, right? If I was just working with the original grammar. Couldn't I just shortcut my way over here and not even deal with that S to epsilon rule? So I'm saving a little bit of work by just directly going to the result that I want. Okay? So that's the main idea here. So here's what we're going to do. So let's copy down our original grammar because we're going to be adding to it. So here we're going to try to eliminate, in quotes, because we're not actually eliminating them yet, epsilon rules. So eventually I want to kill that S to epsilon rule. But anywhere that S appears anywhere else in the grammar, could I have applied S goes to empty? Like up here. Could I apply S goes to empty up there? Where the S0 goes to S? Could I just then apply S goes to empty? Yeah, certainly. So in fact, what we're going to do is we're going to look at everywhere where S appears in the grammar and then add a rule that where that S happens to disappear, where that S is going to empty. So let's look at all those cases. So let's start up here with S0 goes to S. Does the right-hand side involve S? Yeah, it is S. So what if that S happened to disappear? Like if I happen to apply S goes to empty, what would it look like on the right-hand side? Just epsilon. Am I allowed to do that with the start variable? Yeah, so I'm allowed that in only that case. I'll deal with the S to epsilon rule in a bit, but let's deal with this right-hand side. This other one. Does this S goes to that long right-hand side involve S? Yeah, in fact, in 2 places. So how many possibilities are there for both of those S's either staying in there, not necessarily generating the empty string, exactly one of them staying in, or neither of them staying in? There are 4 because I have 2 choices for each of the variables that appear. So what if that first S disappears and not the second one? There's just 2 brackets with the S after it. But it could be equally valid for the second S to disappear, but not the first one. In that case, what would it look like? Bracket S bracket, yes. And if both of them applied the S to epsilon rule, it would just be left, right, curly bracket. Well, everywhere in the grammar where we saw an S, we applied every possible way that that S could have disappeared. So could I now eliminate the S to epsilon rule? Yeah, so now I can delete it. So now, in fact, we're deleting every possible occurrence. We're simulating every possible occurrence of where an S could either be in the grammar or not. So here's the idea. So how do we handle this in the general case? So we're going to call a variable, let's call it the variable A, nullable if, so nullable means it could generate the empty string just by itself. Like if I made that variable the start variable, then it could generate the empty string. Well, what's one really easy way for a variable that could make the empty string? How about just a rule directly to epsilon? So if A makes empty directly, if that's the case, is A a nullable variable? Yeah, because if A makes empty, then A could make the empty string because there's a direct rule there. But what's the other case? Like if we look before for the S0 to S case up here, before we added the epsilon after that, we saw S0 goes to S. Why did we add the new epsilon rule at the end of it? Because we saw S could make the empty string. If S couldn't make the empty string, could I add an epsilon at the end? No, because there'd be no way for that grammar to make the empty string. So if the right-hand side only consists of variables, and each one of them is nullable, could I make the empty string? Yeah, if it's only variables on the right-hand side, and each one of them is nullable, could this new variable make the empty string? Yeah, so that's the other the inductive case that can happen. So A goes to x1, xs, where each xi is nullable. If one of them happens to not be nullable, then I can't necessarily say the variable A is nullable. But if I have determined all of the variables on the right-hand side are nullable, then A is nullable. So in this case, the S here, the entire right-hand side was variables. Every single variable was nullable, the one of them. And so then we determined S0 is nullable. Okay, and then once we know the list of nullable variables, then we can go back through the grammar and add rules for each of the cases where each nullable variable can disappear. So the set of nullable variables in this case is what? What variables are nullable for this grammar? S and S0, because S0 can make empty. So I look everywhere in the grammar where I see an S, I better not see an S0, but everywhere I see an S, and I add a rule for each of the possible ways that S could disappear or stay there. So I'm adding rules to simulate as if those variables may be empty string. And then at the very end, I literally delete all of the epsilon rules. So I'm simulating them with other rules. Okay, any questions on that? So maybe one example and then you can go. Let's see. Okay, let's do this, and then B is epsilon or whatever, and C is epsilon or, actually let's make it a little longer. And let's have D not make the empty string. So is D nullable if this is the whole grammar? No, because D can't make the empty string. Are B and C nullable? Yeah, because they directly make it. What about A? No, why not? Because every variable on the right-hand side has to be nullable. D is not, so therefore A cannot be. But, so now we know the nullable variables are just B and C. So I look everywhere in the grammar. Let's just look at that first rule. But B and C could appear elsewhere. And I got to simulate every possibility of whether B or C could disappear. Well, this case handles when both of them are there. But what about other cases? What if the B disappears and not the C? I'd get CD. What else? What other combinations? BD. Or what other case? Just D. So if I have a particular rule that has S nullable variables on the end, in it somewhere, how many rules am I going to add? 2 to the S minus 1, but 2 to the S roughly. So if I have 4 nullable variables, I'll have 16 rules corresponding to that for all the possibilities that one variable could be there or not. Any questions before I let you go? Yeah.
You didn't finish converting that grammar to a CNF, right? That isn't.
No, I'm not done at all. I have 3 more steps to do, which you'll learn about on Wednesday. Yeah, other questions? Yeah.
Going back to the previous example with S.
The first step or the second step?
Just wondering about the nullable variables.
Mm-hmm.
How come S is a nullable variable?
For which one? Because in the original grammar it made empty.
Oh, you're talking about the original.
Yeah. So right here, what I produced here, that's the final grammar after doing all the work. But I start with the one the grammar right above it. Yeah. Cool. See you Wednesday.